see.
Yeah, in YouTube it is still not showing, I guess.
Yeah, it's not showing yet. Yeah, just waiting. I'm with the YouTube channel open here, just waiting for Sandro to put this on,
Yeah, now
start
it
the
has
streaming.
started.
Yeah,
Yes.
yeah, yeah. Now it start. Yeah, yeah. So, good morning. So today we have the honor and pleasure to have the talk by Santanu Mahapatra. He received his PhD degree from the Swiss Federal Institute of Technology in Lausanne in 2005. For his PhD dissertation, he worked on the modeling of single electron transistors and its co-simulation and co-design with CMOS. He joined the Department of Electronic Systems Engineering, formerly CEDT, at Indian Institute of Science, Bangalore, India, as an assistant professor in August 2005 and promoted to associate professor and then full professor in September 2010 and December 2015, respectively. His research interests include two-dimensional channel transistors, energy-efficient electronic switches, and energy storage at nanoscale. He is the author of the book Hybrid CMOS Single Electron Transistor Device and Circuit Design. He received the IBM Faculty Award in 2007, the Microsoft Research India Outstanding Faculty Award in 2007, and the Associateship of Indian Academy of Sciences in 2009. He's also the recipient of the Ramana Fellowship 2012 to 2015 in the discipline of electrical sciences from the Department of Science and Technology, Government of India. He is a senior member of IEEE. So thank you so much, Santano, for willing and being here to give us the talk. Yes, and now the floor or the screen is yours.
Okay, thank you very much, Gilson, and thank you everybody. So it is good morning for you and good evening, good night for us. And actually, Professor Gilson, me, and there are two more partners from Russia and China. We are a part of the BRICS team, and whatever I am going to tell today, this research work actually, although it is done independently by my team in ISC Bangalore, but it is a part of this project. And it is very unfortunate that I am giving this talk online. We had the research grant to visit each other, and officially from our side the project is just got over last month. We did not get extension, but it seems that Professor Gilson got some extension. So project is officially over, but not the relationship, I guess. And I could have given this talk physically in front of you, but because of COVID, last almost 2.5 years, and but I hope that I will visit your place in near future, and I'll meet you. I mean, I don't know all of you and who are listening to me, and so it is, this talk is online and we have to accept it as it is. And so now, yeah, let me present some outcome of this project that again has been done independently by our group at ISC Bangalore. Okay. Now my understanding is that most of the audience, they are the students. Okay. So maybe the undergraduate or postgraduate student who are just at the entry level of the research, and most of you are coming from electrical engineering, electronics background, correct? Because this talk is hosted by IEEE EDS Society, I guess, and Solid State Circuit Society. Okay. You will see how the electronics, future of electronics, it is evolving. It is no more, we no more talk about silicon, and it seems that the golden age of scaling is over, that just by geometry scaling or simply by folding a transistor and you call it FinFET, it will not work. It is not going to give us performance. Okay. So the performance, the mystery, it is uh, embedded within the materials. Okay, so the materials, research in materials and harnessing their exotic property and apply them for electronics. Okay, this is the future of electronics or nanoelectronics. So in today's talk, I am a expert. I mean, our work is mainly on the device modeling side. Okay, so when we started the career, it was mainly the silicon device, and we know everything about silicon or even germanium or even 3.5. Okay, but as you know that after the discovery of graphene, okay, there is tremendous interest in graphene and beyond graphene two-dimensional materials, and we know very little about their properties. It is still under investigation. People are still working on graphene and they are coming out new and new properties. Okay, and in our research, it deals a lot about this material property, calculating the material property by some computational method, and then find application in the electronics. Okay, so generally, I guess all over the world, even in India and elsewhere, in Brazil also, the usual electrical engineering courses, that is for the undergraduates, the 4 years, I don't know what you call it, baccalaureate, or in our country it is bachelor. Okay, bachelor degree, 4 years bachelor degree of engineering that we have here in structure. Then we have 2 years of master degree. Okay, then one can continue to PhD. So in typical electrical engineering, or you can say EECS engineering, okay, the material property, these are not taught well. Okay, maybe one topic just like that. Okay, but that is a real challenge, I mean, for the electrical engineers who are coming for research in this nanoelectronics, because now you have to deal with new materials, and doesn't matter you are doing experiment or theory, but understanding material is very much important. And in this talk, it deals a lot of material and some techniques to calculate the material property, namely density functional theory, then molecular dynamics. Okay, so we heavily use those techniques, but I understand that might not be very familiar to most of you. So I will not go very detailed in those techniques, but rather I will just show you the result. More importantly, I will give a very broad overview of this emerging area, non-volatile resistive switching. Okay, and the application of 2D materials for this new type of memory. Okay, so that I hope it will ignite some interest to this young mind, the undergraduate, postgraduate student, and you will have an idea what kind of skill set to require. My work is theory and computational, but again, as I have said, it doesn't matter it's theory or computational or experiment. So you need to learn, you need to develop skill set on material science, even you are coming from electrical engineering, and you will appreciate how much secret is hidden in these novel materials and how we can apply them for future of electronics. Okay, so let us start. So first we start with the beginning, the prologue. It is the Van Neumann architecture, the big picture. So Van Neumann architecture and the bottleneck and the in-memory computing and resistive memory. Okay, probably in-memory computing has become a buzzword nowadays, but let us just try to understand. So we start from the, I am in electrical engineering. So, okay, so we start from system perspective. Then slowly as I proceed, I will from system to device, and then I will come to atom. Okay, so it is a system to atom talk, you can say. Okay, so you know probably that the modern computer, for example, from the computer this is a Apple computer. Okay, I am giving this MacBook Pro. It has this latest so-called Apple chip, and the probably all the computers or mobile phones you are listening to this talk, they have a processor, and this processor, it is built upon this so-called von Neumann architecture. Okay, and as I have shown here, so it has two major building block. One is the CPU, where all the calculation, all the mathematics is going on, and then you have a memory unit. Okay, and then it is connected by a channel, we call it bus. Okay, so this is a typical von Neumann architecture, that this, which says that the calculation, that the processing unit CPU and the memory unit, that is the storage, okay, they are physically separated, and they are connected by a channel, we call it bus. Okay, so this channel is very busy, okay, because always you are sending information from CPU to memory and memory to CPU, and this memory is mainly the DRAM. Okay, of course inside CPU you have small memory, right, cache, that is the SRAM, but that is very small, that is very limited. Okay, so mainly we store bigger information in the DRAM. Okay, so this communication is happening, and all the calculations are done by this kind of processor architecture that is right now inside my computer. This is the von Neumann architecture. Okay, so what is the problem? We have been using this architecture for years after years, and suddenly people are talking about non-von Neumann architecture, and why so? Okay, again because it is the application. Okay, and our industry, semiconductor industry, the economy is driven by the application, and nowadays everywhere you hear one word only, that is AI ML. Okay, so this AI ML based algorithm, when we try to execute, okay, that is deep learning, the, you know, I'll talk about it. So when we try to execute this algorithm in our von Neumann based architecture, it becomes terribly inefficient. Okay, and so that's why, because now our world is moving towards this neuromorphic computing, AI ML, everywhere we apply it. Okay, and even you will see that I will end up, this talk deals a lot of with molecular dynamics. Okay, I will end up my talk is something with the emerging molecular dynamics approach, that is called machine learning force field. Okay, so there is also we are applying ML, it is everywhere. Okay, so the economy is driven by this thing, and even in Apple chip, in the computer, in the mobile, you have something called neuro chip, etc. Okay, now here let's try to understand the problem. So on my right hand side, I guess, I mean, some of you have basic knowledge of the neural network, right? So right hand side at the top, what we have, it is a single neuron, that is also known as perceptron. Okay, so how does it work? So output, it is a summation of, these are the x are the input. Okay, this is the input vector, and w's are the weight. Okay, so the summation, that is wj xj, okay, when it is lesser than threshold, then the output will be 0, and when it is higher than the threshold, then the output, we say in the language, the neuron will fire. Okay, so output will be 1. Okay, so this is simple perceptron. Okay, now you can put in the bottom figure, you can put many such perceptron, okay, as a layer. So these are called layer in a neural network. Okay, so there's one layer and two layer, three layer, okay, then finally output, and these layers, they are connected with each other. So here goes the input, the number of input probably the same, say x1, x2, xn, and each of them has weight. Okay, each of this line is weight, w1, w2. Okay, so here you can see ultimately the output, it will become a vector matrix multiplication. Okay, so output, it will be vector. So x1, x2 inputs are vector, and all the weights, okay, they come in form of a matrix. Okay, so all this neural network is nothing but a vector matrix multiplication, that it comes in a matrix form. Okay, now you try to understand the problem of this von Neumann architecture. Okay, so this calculation, I mean, this is the product and the summation that is going on within the CPU. Okay, and all the inputs and the weights, they are stored in the memory. Okay, just to do this multiplication and summation, you have to bring this all these weights and inputs to the CPU, and just do the calculation. You calculate the output, then again you send it back. Okay, so this to and fro motion, it is becoming for this kind of application. Okay, now there is something, in neural network, we say training the neural network. What is neural network in very easier sense? Say this output, it is a function of input. Okay, so output is a function of x1, x2, x3, x4. Okay, what neural network is doing, it is generating a complex mathematical function which try to map the input with the output. Okay, and so the perfect matching, you have to choose the weight correctly. Okay, and the process of this finding the weight, okay, so that input properly matches with the output with your training data, it is known as the training the neural network. There are different algorithm, I am not going to that. Okay, but all of this training, it requires this to and fro motion of the memory. Okay, so for this special type of application, what is happening, this bus is becoming too busy, and there is too frequent communication. Okay, so two things is happening, the power dissipation, more the flow of the data, power dissipation would be more. So power dissipation is more, and because of the bus has certain width. Okay, so this travel of the data, it has become very slow between CPU and memory. Okay, so I mean, as you can see, I mean, we have been using this architecture for years after years. Okay, but right now there is so much emphasis on this AI ML and their algorithm. Okay, so people found that this architecture is becoming more and more inefficient to execute this deep neural network based algorithm. Okay, so the solution is proposed. It is called non-von Neumann architecture or in-memory computing. Okay, so here the computing, the idea is that you embed the CPU and memory, you embed it together. Okay, so that's the thing that is called in-memory computing. In a simpler way, I can explain you in this way. Say, you know what is called combinational logic, right? You have studied it in your digital logic. So combinational logic. So we have in digital circuit, you have studied combinational logic and sequential, right? So sequential logic is nothing but memory, and you have combinational logic. So you have x1, x2, these all are Boolean variable, and you have some output. Okay, so and they have some relation, right? And then this relations, it could be written and or all these gates. Okay, now so there the real computation is happening, right? Now if you think that combinational logic is nothing but uh, what is that, it is a truth table, right? And instead of doing real computation, this and or xor, okay, so you have the your truth table. Why don't you just take the truth table and put it in the memory? Okay, so replacing the combinational logic by a truth table, and you just keep it in your memory. Okay, then in this process probably you can completely eliminate the combinational logic. The design is very computation, the design is complex. Okay, the delay, okay, you have different delay path, etc. But memory, you can see they have symmetric architecture. Okay, so this is a basic example of in memory computing. Okay, so here you saved. So if you can do this thing, then the to and fro motion from the computational and the memory you need, it could be avoided. Okay, so the advantage is that, as I have written, data stored and processed, they are simultaneously high speed, energy efficient, and thus it is very useful for this kind of neural network or neuromorphic computing. Okay, so naturally, so it has this kind of architecture, okay, that we call crossbar switch. Okay, so it is like a matrix type of architecture, and each of this crossbar, that is, you can think about like this. Okay, so each of this crossing point, you have a memory unit. Okay, so you store information here and you compute it here. Okay, so this kind of memory, okay, it is known as, in general, it falls in the category of resistive RAM. I will tell you why the resistive. But it has several subcategories. Subcategory means these are different technology, but ultimately it leads to this kind of, this is the circuit symbol. Like register has a circuit symbol, like this one. So this has this kind of circuit symbol that we call resistive memory. Also it is known as memristor. Okay, so it has two state. One is low conductance, that is logic 1, and another, it is high conductance, okay, that is logic 0. Okay, so it is unlike, see here, two things here. In in your CMOS logic, or any digital logic, okay, that we have studied, right? CMOS inverter, or even it is a BJT based logic. Okay, there, in our regular, in your classical computation, or the classical integrated circuit, okay, there, this is very important, we store information in charge. Okay, so presence of charge, it is either, you can say, 0, and absence of charge, it is 1. Okay, it is up to you, you can do it opposite also. Okay, now you see what is information. I mean, what is this Boolean algebra? Okay, this is all mathematics. You have 0, 1, then you have lot of mathematics. Okay, and god, and gate, NAND gate, etc. Okay, but you need a physical media to represent what is 0. I mean, 0 should be represented by some, it is not a something vacuum or idea. Okay, it has to be represented by some quantity, we call it vector. Okay, so charge, where we encode this information 0 and 1 in our classical circuit, everyday circuit, electronic circuit. Okay, now problem is that we cannot directly measure the charge, right? In order to measure the charge, what you have to do, you have to convert it in voltage, right? So if you remember your very basic electrical engineering circuit theory course, so we study how to charge and discharge a capacitor, right? It has this rise time, it has this fall time. Okay, so 0 to 1, so the thing is that it needs some time to charge a capacitor, 0 to 1, and time to discharge, 1 to 0. Okay, and here, so we, when you store some charge in a capacitor, there would be a voltage buildup. Okay, and so the presence of charge, actually it is felt through voltage. Okay, and the absence of charge, it is also felt through voltage. So we cannot directly measure the charge, you have to convert in the voltage. Okay, that is actually major problem of all of this charge based logic. What is the problem? There is twofold. First, again, what I have told, you need a certain time to charge a capacitor and discharge a capacitor. Okay, in your basic digital logic course you might have read the setup time, hold time. Okay, so when you are designing a digital circuit, you have to take care of this set time, hold time, setup time, and the frequency of your circuit, it totally depends on this thing, right? If you have a ideal situation like zero setup time, zero hold time, then our circuit could have been very very fast. Okay, but unfortunately that is not, because any capacitor, it takes some time to get charged and takes some time to get discharged. So this is one problem, the delay. Second is, as you know in your basic course in CMOS inverter, that in a circuit theory, that when you charge a capacitor and when you discharge a capacitor, each cycle, each process, you lose energy. Okay, you know this thing, it is called half CV square. Okay, and as you know in CMOS inverter, we say that the dynamic power dissipation, it is the major role. Okay, because again same reason, you are charging the output load capacitance half CV square loss and discharge it half CV square loss. Okay, then you, how frequently you are doing it, so the frequency term is coming. So C VDD square frequency, right? That is the dynamic power dissipation, right? So that is, and that is something very fundamental. Okay, now when we try to make a low power circuit, okay, what we are trying to do, we are trying to cut down two things, VDD. Okay, because it is VDD square, if you can cut down VDD, that is we call supply voltage scaling. If you have studied CMOS scaling, probably you know what I am talking about. Okay, that is the VDD scaling. Okay, so we have this two type of scaling, right? One is constant VDD scaling and constant field scaling, right? And when we do constant field scaling, then we scale down both the VDD and the geometry in the same proportion, so that the electric field become constant, right? You might have read it. Okay, so that is something ideal thing that we would like to do it, but we cannot do it. Why? Because if you cut down VDD, at the same time you have to cut down the threshold voltage also. Okay, otherwise if you don't do it, your on current, it is VDD minus threshold voltage. Okay, if you cut down VDD, if you don't cut down the VT, your threshold your on current, it will collapse, then your delay will increase. Okay, that we don't want. So whenever I am cutting down VDD, I have to cut down the threshold voltage. But you probably know that your subthreshold current and the off-state current, it is a exponential function of the threshold voltage, right? So when you cut down the threshold voltage, your off current, it will increase exponentially. Okay, so now if I don't know if you are aware about ITRS roadmap or IRDS roadmap, if you go and see it, in the recent time, the threshold the VDD scaling has already been kind of saturated. Okay, and actually we cannot cut down the VDD lower than 0.6 volt. Okay, 0.55 kind of that. Okay, because of this problem. Okay, so VDD cannot be cut down, and now it has almost been saturated, the VDD scaling. Now the CL, okay, CL, it is the load capacitance. Okay, and if you know your DRAM architecture, it is 1T 1C, right? So you have one transistor which is connected to the capacitor, right? Now actually it is like that, you cannot, and I don't know, I don't have any picture here. If you have seen really how the DRAM capacitance look like, it looks like a trench, okay, which is very very deep. And the technology is like that, they are required, I mean there is this sense amplifier, right? It will sense if the capacitance you have charge and you don't have charge, it is logic 0 and logic 1. In order to sense it, you need a minimum amount of critical charge. Okay, below that it cannot sense. Okay, so that's why in order to maintain a minimum critical charge, so you have to preserve a minimum critical capacitance. Okay, so this DRAM capacitance, it is not scalable. Okay, so these are the problem, 2 3 things with the DRAM. Okay, or you can say these are the problem related to encoding information in charge. Okay, the power dissipation problem, you cannot scale down the capacitance. Okay, so overall it is affecting, I mean, your memory architecture, that always we would like to have a very dense and very fast memory. Okay, now so the idea of, you know, encoding information in charge, we have to move out. Okay, and we have to look for other vectors, okay, where we can encode the information. Okay, now people are doing research in different type of vector. Okay, probably you know one of this thing is that electron spin. Okay, up spin, down spin. And so you have the magnetic RAM. Okay, so depending on the alignment, it is consisted of two ferromagnetic material and in between one ordinary material. So you know the ferromagnetic material, all the spins are aligned either up or either down. Okay, so if the top layer spin alignment and the bottom layer spin alignment, they are in the same direction, then it offers very low resistance. Okay, but if it is opposite, it offers very high resistance. So this is also one type of resistive memory. Okay, but you see the difference here. I am encoding the information not in the charge, okay, but in the electron spin, that is another vector. And the other type that we will discuss, that is the, you know, resistive memory, we will say filamentary based memory or phase change memory. Okay, these are different class. Okay, here you will see that these are basically a capacitor architecture. It has MIM architecture, that is two electrodes, metal electrodes, and in between we have a material. Okay, when you apply a electric field, that is, it is a capacitor basically, when you apply a voltage across the two plate, because of the electric field, the material itself, it changes. Okay, that falls under phase change memory, or our filamentary memory is also, we'll discuss this thing. So here I am encoding the information not in charge, but I would say in the material chemistry. I am changing the material by electric field, and as a result, what is happening, the resistance of this two terminal device, it is changing. So it will go to in two state. It can also go, we will see, in multi-state. Okay, I don't know if you have ever came across of this something called multi-valued logic. Okay, whatever in digital logic we study, it is mainly binary, right? 0 and 1. But there could be, you know, the concept could be extended and we could have multiple valued logic. In between, say, 0 and VDD, I can have several steps. Okay, so that is another way to pack information in the unit area, more information. Instead of going from binary, instead of using binary, we can use multiple valued logic. Okay, so in this type of device, you will see we can have multiple stage and we can have multiple valued logic. And another thing, this type of memory, most of the time, it is non-volatile. That means if you make it, I mean, we say if you, you know, turn this device, make it logic 1 and switch off the power, it will preserve logic 1. So these are non-volatile memory. Okay, so there are this kind of several, you know, advantage of this kind of memory. Okay, that is non-volatile memory, and it is a two terminal device. This kind of devices is also known as memristor. Okay, now as you can see, the concept, it is very very different from our usual charge based, you know, CMOS circuitry. Okay, now you have a two terminal device which you can encode, you can program it to be a logic 1 high resistive mode. Okay, and or low resistive mode, you can call it logic 1 and logic 0. Okay. Now throughout my talk, okay, I will leave several references, okay, so that if you are interested, you can go through it for your further reading. Now here is one example. It is a magic memory star aided logic which you can go through. It is a nice article which shows that using this memory star, okay, how you can implement our regular AND gate, OR gate, NAND gate, or even combining them a bigger logic, a bigger circuitry like marks, etc. Okay. Now here is a, so once more thing, that this memory star was the concept. It was first proposed by Professor Leon Chua, as we probably know, and it was first demonstrated by, that is the missing register, right? You might have read about it, and it was first demonstrated by HP Lab. Okay, so there is one this nice book. I have bought it and I find it very nice. I mean, it is very good for undergraduate student. This is a new area, you need to learn it. So it starts from very basic, okay, mathematical foundation of memory star, then go to the technology, then talks about circuit, then it talks about different kind of application, including the neuromorphic application. Okay, so this is a good book to read for further reading. Okay, now I come to the resistive memory part. Okay, so here is the, IV characteristics of a typical memory star or resistive memory. So it has, first you follow the red line. Okay, if you follow the red line, so x-axis is the voltage, and it is a two terminal device, right? You apply voltage and you measure current. So when you are, say you are at 0, okay, now you are increasing the voltage. Okay, so it behaves just like a normal resistor. Current is kind of increasing, kind of linearly. Then what happened? There is a sudden change in the resistance. Okay, we call it set. Okay, like your flip flop. Okay, you set and you reset. Okay, so it will jump. Okay, the current value or the compilance, we say, it jumps from, it is like a discontinuous jump from one state to the another state. Okay, then if you keep on increasing the voltage, it will hold this state. And more interestingly, if you now start reducing the voltage, it will not come back to this path, right? It will rather go, it will hold this value. Okay, it will hold this value, and then it will hold it. Okay, but at zero voltage, what will happen? I mean, you cannot have current with zero voltage. Okay, so at zero voltage, it will come to zero. Okay, now again, if you switch it on, okay, and apply, try to measure the current, it will not show this current, it will show this current. So it is holding the previous state. Okay, now how I can reset, I can bring it back. So for that, you have to go to the other direction. Okay, so if you go to the other direction, then again it will reach to this state, but in the opposite current. Okay, then if you keep on increasing the negative voltage, then this, it will go to the reset, it will come back to the previous state. So you can say that this device, it is switching between two conductance state. Okay, and it has a memory effect. Okay, that is the hysteresis loop. Even you withdraw the voltage, it can hold your previous state. Okay, so this is the basic idea of a memory star or resistive memory. Okay, now how to implement it? Okay, people have implemented, or they have built such kind of device. I mean, this is the idea, but how to build it? There are different kind. There are mainly, you can categorize it into two major things. One is called electrochemical metallization memory or filament based. Okay, and second is that valence change memory. Okay, here, so the basic idea is that you have two metal electrode. They could be in same metal, different metal, and in between you have a oxide. Okay, oxide made upon, these are transition metal oxide. Okay, generally TiO2 is used. There are other oxide is also used. So these are the amorphous material. Okay, so what happens when you apply the voltage? Okay, this metal atom, it migrates and create a filament. Okay, so you see, when it is just a capacitor, two metal electrode and you have a oxide. Okay, so if we apply voltage, there would be no current or very minimal current, some leakage current, so you are at the off state. Okay, but if you keep on increasing the electric field, what happen? I will show you a video now. It will create filament. This metal atom, they will migrate like this, and it will create a bridge. When the bridge will you know that is called conductive bridge memory also something. So you create a bridge between two metal electrode. Okay, so that then the device, it will get turned on and it will hold this state. Okay, so when you apply, as you can understand, even you withdraw the voltage, the bridge will be there. In order to break the bridge, you have to reset the device. You take the voltage in the other side, you change the electric field, this the bridge will be destroyed, and you come back to the high resistive state. Okay, so this is one thing, and here you can see a video. Okay, this is from the paper Nature Communication, and they have done in situ video. Okay, so here you can see how the filament is growing. Okay, real video, and it creates the bridge between two electrode. Okay, now this is one kind, that is filamentary memory, and there is another kind. It is because of the oxygen vacancy. Okay, so you have oxygen vacancy and they pile up and they create similar kind of bridge. Okay, so here comes the material chemistry part. When there is oxygen vacancy, okay, it creates a positive charge. Okay, that could be analyzed by different kind of theory, and so it creates a filament. Like it is not like this filament, but it creates a bridge. Okay, so that is called valence chain memory, and this is the filamentary based memory. Okay, so the basic idea is same, that it is a capacitor. Initially there is no connection between the two metal electrode, but if you apply electric field, then depending on what are the material you are using, there could be a bridge between the two electrodes and make the device conductive. And this bridge is non-volatile. That means if you remove the electric field, the bridge will be preserved. Okay, so the state, memory state, or the resistance state, it will be preserved. Okay, you have to reset. You probably have to apply a negative voltage. Okay, high negative voltage to break the bridge, and joule heating also play a big role. Okay, so these are the memristive device or non-volatile resistive device, and this kind of technology I will show you. It is now near commercialization. Okay, so now it has some issue. Okay, like it requires very large forming voltage. Okay, this is called forming voltage, because we always want to scale down the VDD. In order to make this thing bridge happen, it seems that you require high forming voltage. Then the scaling. Okay, scaling is that it appears that it is very difficult to reduce the distance between two metal electrode. This is another thing. And so we will see how this new 2D material can overcome some of these challenges. Now, other aspect of the resistive memory. One thing that I was trying to tell you, see, unlike a capacitor charging, our classical digital logic. Okay, so here there I am encoding information in charge and I am storing the charge in a capacitor. Okay, the storing and discharging a capacitor, it is very deterministic procedure, right? You can just guarantee it. Okay, precisely when you can calculate the delay time, the rise time, fall time. But here what is happening, as I told you, here the material chemistry. Okay, there is some electrochemical reaction is happening, this filament is forming. Okay, this chemistry, that is some chemical reaction is happening, it is always stochastic, random in nature. So you cannot guarantee. It is a common problem in resistive memory. There are many and many papers. Okay, say if you have, say, fabricated a crossbar, say 100 resistive memory, not all of them it will work in the same way. Okay, because some chemical reaction is always going on inside the device, so it is always stochastic in nature. Okay, now that is one problem of this memristive devices, and when you build up a circuit, you have to take into account this stochastic nature of these devices, and your circuit topology, it should be such that it can taken care of. Okay, this problem is taken care of. So from the circuit design point of view, so this is a area which is emerging, and it is very interesting area. Okay, because at the same time, you can work at the circuit side. I will tell you about more, because this type of memory is known also analog memory. Okay, in contrast to our usual DRAM, which is the digital memory. Okay, so how to read from this memory? Okay, just the memory design itself is a challenging thing for this kind of new type of memory. Okay, so this is an area where we can work from material to circuit to the system in the all area. It has so many challenges. Okay, and also new application. Often you will see in even in this high impact journal in Nature Communication, people are showing different kind of neuromorphic application using this resistive memory. Okay, and but you can take advantage of the stochastic nature. Like you will see many papers, they are using the stochastic nature to use this memory as a random number generator. Okay, where, because nowadays security is a main issue, and for secured communication they are based on this random number. But a true random number generator, it is really a challenging. Mainly in the digital circuit, you use the shift register to make a random number generator. Okay, but they are not true random number generator. Okay, they are all a pseudo random number generator. Okay, but these are when you generate random number from physical hardware, there is a possibility you can get a true random number generator. Okay, so here is again I am leaving some references for you. You can read, that is the stochastic nature of this random access this resistive memory, and how you can utilize it for different application, and when you design big circuit using this memory, how to take care of it. Now, towards the commercialization, there are some startup like Crossbar and big company like Hinks, in collaboration with HP. Very soon, we expect to see this technology, okay, available for big circuit design or the system design. They will be available, commercially available. Okay. Now we come here to our our main topic, that two-dimensional material-based resistive memory. Okay, so here the idea is that the architecture, it will be same. Okay, MIM. Okay, metal insulator metal, but instead of insulator, our plan is to replace this bulk insulator, that is the transition metal based oxide, with a 2D material. Okay, and more precisely semiconducting or insulating 2D material. Okay, so that we can gain over the scaling. Okay, and it could have many other advantages. Okay, so the first demonstration, it was almost how many years? It is going 8 years, right? Or yeah, 7 years back. Okay, so that is the lateral device. So you have a flake, and at the two end you put the metal electrode, then you measure. So here also you can see this kind of resistive memory action, that is the hysteresis loop. Okay, so this was the first work which immediately attracted lot of attention. But this work does not take into advantage the major, you know, property of the 2D material, that it is 2D. Okay, that is, it is atomically thin. Okay, it doesn't have any thickness, or thickness is atomically, the thickness is atomic. Okay, so it doesn't take, because they are putting electrode at the two end. Okay, so the first, this is the lateral MEM device. So the first vertical MEM device was reported in 2016, just after 1 year. So there they stack, they are taking into account, they are taking the advantage of the thicknessless property of this 2D material. So here, just MOS2, one of the commonly used 2D material, it is sandwiched between two metal electrode. Okay, and they demonstrated this same memristic behavior, the hysteresis loop. Okay, so this is another example. It is from our another collaborator from the same project, and they have demonstrated the same behavior with HBN. So they have changed the material, right, from MOS2 to HBN. So these are multi-layer. And another thing, as you can see, they are showing different states. Okay, so as I told you, that these devices can also be used for multiple valued logic. You can see the states, and they are very reproducible. Okay, iterative. Okay, then came something very, very significant work, and our model is based on this device that nobody thought. I mean, all of this work, they are multi-layer. Okay, so they just sandwich, they just put a single MOS2 layer between two metal electrode. Okay, and they show this kind of hysteresis effect, the memristic effect. Okay, so this one nobody expected, because these materials are so thin. If you make this device, probably it will be leaking like anything, and it will behave just a simple resistor. But it is also showing this type of memristic behavior. Okay, so we mainly worked on, we developed model for this kind of device, just to find out that how this device is working. Okay, and if this memdistance is a inherited property of this 2D material, because you can understand these all are crystalline material, unlike this oxide based memristor, bulk memristor. In oxide you have lot of void, vacant space, and through which this filament can grow, but these are pure crystal. Okay, and so we don't expect any kind of filament formation here. So what is going on? Okay, here there is another example I will talk about. It is MOT2, another material. It is from Purdue. Okay, and this is for Texas A&M. Okay, and they also show this kind of, so you can see we are changing different kind of material, MOS2, then HBN, MOT2. Okay, this group has shown different kind of material, WS2, etc. So people have demonstrated experimentally, um, you know they have achieved this memristor behavior. The architecture is same, that is two metal electrode, but they are putting different 2D material in between, and they are observing this kind of memristor behavior. Okay, but the thing is that we try to explore in our project, that from where this nature is coming. I mean, why it is showing this memristor behavior. Unfortunately, starting from 2015, this 7 year, right, you will see a tons of paper, because probably this is a device, it is easier to fabricate. Okay, this is just two metal layer and you put something in between. Okay, so lot of experimental demonstration, but very little work going in understanding from where this memristor behavior is coming, because definitely we cannot apply our theory of the bulk memristor device, which is built upon oxide, okay, transition metal oxide, to this kind of device, because here this insulator, it is made upon very good crystalline material. Okay, so let's see, there is little bit work now people are doing, okay, just to go inside to get some insight, okay, how these devices are working. Okay, now again I focus on this work of from Texas A&M University. They call it atomister because they have simple one atomic layer, and it was their first demonstration by MOS2. If you are not aware about MOS2, so this is the unit cell. This purple is molybdenum and sulfur is yellow. So two sulfur and one molybdenum, MOS2. So mono layer. Okay. And here they observe this type of usual bipolar device, that in order to reset the device you have to apply negative voltage. Okay, also they show some kind of unipolar device. Okay, that is, you can reset the device by applying positive voltage also, little positive voltage, it will reset the device. Okay, but you have to push high current. Okay, now this device, okay, some people can say there is some defect inside because of which it is happening. In 2D material there is something called grain boundary, it has grain, and from grain boundary, because of grain boundary, the this memristor behavior is happening. But they have fabricated this device for different type of sample. Okay, they have exfoliated sample, they have growth sample, they have this litho free transfer free device. For each of this sample they are observing these characteristics. Not only that, they have changed the electrode, they have gold electrode, they have silver electrode, they have many other electrode also. Everywhere they are observing this behavior. And most fascinating thing, they are observing this behavior with a graphene electrode. Graphene is chemically inert properly. So here someone can claim, like this author has also claimed, that when you are having this gold silver, then probably atoms from the electrode they can remove and then can get stuck in some defect. Always this MOS2 has some sulfur defect. Okay, so atoms are getting removed from the electrode and get stuck, get attached to the defect, sulfur vacancy defect in the MOS2. From there, from this atomic movement, because of which this memristor behavior is happening. Okay, but this cannot be applied to this graphene electrode, which is completely passive. Okay, so we developed some theory using molecular dynamics, okay, which can explain, okay, from where, why this 2D material has some intrinsic memristive property, and why they are showing such memristive effect even the device is built upon electrode like graphene, which is completely passive in nature. Okay, now, as I was telling you, like same group, Texas A&M, they have published many papers. So they have even shown that they say that single defect memristor or world's smallest memristor. So they have used this tip of AFM, okay, and they are showing this memristor effect, and they have taken some spectroscopy and try to show that really the gold atom has been moved from this tip to the MOS2, and because of which the memristor nature is coming. Okay, but there are other results also. Okay, let us see this using this Purdue group MOT2. Okay, they came up with a completely different theory. Okay, so they show using spectroscopy that this 2H MOS2, so this 2D material comes with different phases. Okay, so normally it is the 2H phase. Okay, when we apply electric field, this phase get changed, this is called phase change, and it gives something called HD phase. You can see the atomic arrangement has changed. Because of this atomic arrangement change, that there is a change of this resistance. Okay, then there is Counterexample by Stanford University group. They even don't believe their theory. They are saying it may happen for some special cases, but it is not always the cases. Okay, so you can see there is a contradiction of the theory, and there is lot of experimental demonstration of memristor based on this two-dimensional material, but why it is still happening, why it is happening, from where this behavior is coming, it is still not known. Okay. Now, what we have done, so this is our paper. Okay, in our project was mainly based on this memristor two-dimensional material based memristor. We are four partner. We are working in different aspect of this memory. So here we are developing in Indian group. Here we develop some theory, and what we say that atomic model of this 2D material based memristor. Okay, so it has published last year in this Nature journal 2D materials and application. Okay, so I will now try to explain it, but again I am telling you it involves a lot of tools which is used for material modeling, and it is a IEEE talk, and most of the audience I believe from electrical engineering background. So I will not go, I mean these tools, I mean I expect it is not very familiar with you, so I will not go in very details, but I will give a very primer, okay, of these two things, density functional theory and molecular dynamics. Okay, so that you understand a little bit at least what is going here. Okay, so first is that we give a primer on density functional theory. Okay, for the people who are not aware about it or has very little knowledge. Okay, so what and why? Okay, so what is density functional theory? So it is a Nobel Prize winning word. It was first proposed by Professor Walter Cohen. Okay, so Nobel Prize in Chemistry 1998. So what is this? I guess all of you have done a basic course in quantum mechanics, and you have studied Schrödinger equation and the solution of the Schrödinger equation for a single particle in a box. Okay, so it is very simple, right? You can get an analytical solution, you can get all of this energy state and the ground state and the wave function, all of this thing analytically. Okay, but this problem gets terribly complicated and computationally challenging when you try to solve the Schrödinger equation for many particle system. Okay, what this gentleman did, he proposed a approximate solution to the Schrödinger equation of the many particle system, and that is in nutshell it is the density functional theory. Okay, and it is so popular and we are using it. Why we are using it? Because it gives very good result, and good result means it explains many experimental observation. Okay, so where we apply it, we apply it to calculate different properties of a crystal. Crystal means a material. What is crystal? It is a periodic arrangement of the atom. So if a periodic arrangement of atom is given to you, okay, using this theory you can calculate several interesting things, like all the electronic properties like band structure. Okay, electron band structure, phonon band structure. So when you get the band structure, then what you can get everything. You can get the band gap, you can know it is direct or indirect. Okay, you can get the effective mass. Okay, for the phonons you know the acoustic branches. Okay, from the slope you can calculate the thermal conductivity. Okay, it is possible to calculate even more complex property like optical property like dielectric constant. Okay, that is very useful for electron device application, correct? And also different kind of chemical property, like you have a crystal, they are forming a bond. Okay, the quality of the bond or nature of the bond, how much covalence is there, it is ionic or covalent, how much ionic, how much covalent, and the charge transfer between the atoms. Okay, so different properties it can take. Okay, there is tools, of course. Okay, you don't have to write the code. So most popular tools I have written here, two tools. VASP, which is semi open access, it is developed by the University of Austria. And second one is the quantum espresso, that is more commonly used because this is free tool. Okay, and there are many more. And here something I have put here, that is nature. It is in the year of which I forgot, 2016 or something. They came out with something called paper mountain. Okay, that means till that date, whatever paper has, how many paper has been written in all area, if you just pile them, it will probably reach, Everest. Okay, that is the paper mountain. And then if you take top 10 most cited paper, within this top 10 you will get two paper, okay, which is based on DFT. So you can understand the importance of DFT. That is not discrete Fourier transform, but it is density functional theory. It is so popular nowadays. It is now because our computer power has increased. Now we have GPUs, etc., and our computational technique, parallel computing, all of those things, has we have made major advancement. So using the DFT, we can computationally design several material. We can, because we can screen, we can design a vast amount of material. If you try to do it experimentally, it will be impossible to do so many materials, or it would also be very expensive. Okay, so DFT has become nowadays a de facto tool for material research. And even if you read nowadays experimental paper on 2D materials, you will see at the end they put some DFT based analysis. Okay, because it will give you atomistic insight in each atom what is going on, which you cannot probe by very sophisticated, the most sophisticated instrument that you used in experiment. Okay, and it gives so good result that we trust this tool. Okay, second primer, molecular dynamics. That is the main thing. We used both of them and it could be combined. Okay, so what is that, it is for? So what it is used, that we use it to study movement of molecules at the atomistic level. Okay, and again it is important to complement experiment for designing material. So molecular dynamics, it has several application. Especially it is used in biology, drug discovery, protein folding, etc. A lot of in biophysics you will see, and also in material science. Okay, now what it is, that you have a set of atomic system. Okay, and you have some force. Okay, force we will discuss what kind of force, and if you apply force, then how the atom will move. Okay, so this is simulated by this molecular dynamics. Okay, how it is done? So we have a set of atoms, so we can define an initial state, then we can calculate interatomic force. This is very crucial. I will talk little bit on it. Okay, how to do that? There is two approach, classical and quantum mechanical. Okay, so once you have the force, you can calculate the acceleration. Okay, then if you know that, it is simple, Newtonian physics. Okay, if you know the acceleration, you can find the new position and velocity, and then you can iterate. Okay, so in this way we can find the trajectory of the atoms. Okay, now we come to this point, it all depends, the accuracy of the calculation, it totally depends the quality of the interatomic forces. And there are two options. Okay, first is the classical option. Okay, classical force. Okay, we call it classical MD, molecular dynamics. So here there are two atoms, two particles. We consider only two forces. One is van der Waals force and one is charge, Coulombic force. And they are written by this equation. Okay, or also we call the second one, you can say it is Coulombic force, and the first one we call it Lennard-Joule potential, LJ force. And these are parametric. Okay, so DFT, as you can see, it is a first principle based. Okay, why we say first principle based? Because you need to know just the crystal structure. What are the atoms are there? It is sodium, magnesium, potassium, and their position. That is the thing. Okay, and we can calculate all the properties, so we don't need any other information. But in classical MD, this parameter RJ, RM, it has to be calibrated against some experimental data or DFT. Okay, so advantage is that it is very very fast. Okay, you can do very large system. Okay, unless you do a very large system, it is not practical. If you do it for 110 atom system, those are very small. Because if you go to biological system, they are very big. A big a protein molecule or DNA, they have double helix structure, they are very big. Okay, so it is fast but not accurate because it is empirical. Okay, and it is not versatile. Versatile means you fit this system to a particular you fit this equation for a particular system. Since it is semi empirical, you cannot use it for another system, you have to refit it. Okay, so it is not versatile. And the key point is that this, we say this classical MD, it is non-reactive. Okay, when say it is just attraction and repulsion, okay, that only it can capture. But if two particle or two atoms get attracted and they get form a chemical bond, that is a chemical reaction is happening, so it cannot capture it. So this kind of classical MD, we say it is non-reactive. So this information is very important to understand our work. Okay, because in our work, okay, to understand what is going within memory state device, we cannot use it. Okay, what we have used, I will explain now. It's called reactive molecular dynamics, which can also take into account these two atoms are coming together and they form a bond. Okay, that is the reaction, that is the chemical reaction, that is called reactive molecular dynamics. So this is one thing. And another thing is that the most rigorous way, that is the interatomic force, if you are calculating by solving the Schrodinger equation, that is you use the density functional theory. Okay, so you can understand that is more versatile. Okay, you don't need any fit parameter. Okay, it is applicable to any system, it is very accurate. Okay, everything is fine. Okay, but what is not fine is that it is the computational cost, because it involves the solution of this Schrodinger equation. Okay, so the computational cost is very high, so it cannot be deployed for large system. Okay, I mean, this ab initio molecular dynamics package is already there in VASP, Espresso, Castep, etc. But it is limited to only few hundred of atoms. Okay, so of course you cannot do it any practical device. Okay, using this technique. Okay, so here, how to bridge this gap? So here, as I can show, there is classical MD, ab initio MD. Classical MD, it can handle larger number of atoms and you can go for larger time step. But because of the computational cost, it is limited to this corner and it is that corner. Okay, so we need to bridge this gap. So if you move to this side, okay, your accuracy is increasing. Okay, but at the same time the computational cost is also increasing. Okay, so how to bridge the gap? Okay, so that is the thing. The one way to bridge the gap is this technique, which is developed by Professor Van Duyn group in Penn State, probably. So he developed something called reactive force field. Okay, as I have, again, let me not go in deep details, all the references here. So when two atoms are interacting, it takes into account both the bonding and the non-bonding interaction. So it can explain the chemical reaction through the molecular dynamics. In one word, it is like that. Okay, but the problem is that it is also parameterized. Okay, so you have to tune it to a particular system, and only you will not find many paper, only few paper are there outside this group who has some calibrated, some reactive force field for a any new system. Okay, So they have a startup, okay, and they released reactive force field for certain material. Like, we are lucky we got a force field for MOS2, but now we are trying to investigate the other material, and there is no force field, and we are trying to develop it by ourselves. There are certain tool, but it is very difficult to do. Okay, so that is one biggest challenge of the reactive force field. But if they have developed a potential for a material system and released it, then I will show you, you really get very good result. Okay, people have already applied this reactive force field to understand. I have given here, you can see this is from Purdue probably. They have explained how this resistive switching happens in this bulk oxide based device. Okay, so here you can see the filament formation. So all this has been simulated by this reactive molecular dynamics. You will not get such result from this normal non-reactive classical molecular dynamics. Okay, so this is the first application of reactive force field to understand the uh, resistive switching in the bulk oxide based memory star. Okay, it is in nature material. Okay, so now I will talk about our work where we have applied the reactive force field to find, okay, what is, to get some insight of the resistive switching in monolayer MOS2 based memory star. Okay, so there we can develop. Now you can see we are going at the atomic level. Okay, now I will not go very deep. Okay, it will be too much probably. Okay, so I will just give you just the outcome. So this is the monolayer MOS2 and with sulfur vacancy. It is found that naturally found MOS2, most of the time it has sulfur vacancy. Okay, then this is the major takeaway. So this is the density of state of a MOS2, okay, with a sulfur vacancy. So you can see that on the Fermi level there is no state. So that is semiconductor. MOS2 is a semiconductor, and this is the semiconductor gap. And here you can see one stray state came. Okay, so this state will not be there if there is a sulfur atom is there. It is because of the, it is a state, okay, because of the absence of the sulfur atom. Okay, now this state is quite far from the Fermi level. Okay, so we don't expect that this state it will be filled at room temperature. So this state, okay, because of the sulfur vacancy, it cannot contribute in the conduction. Okay, then what we demonstrate by molecular dynamics, if you apply electric field, then I will show you the video. This sulfur atom, it pops up. Okay, this is called popping theory, and it gets stuck at the middle, at the symmetric position. Now, again, if you calculate the density of states of this system, then what you see? You can see a state just on the Fermi level. So state at the Fermi level means it has metallic, it is metallic, right? So metal has states at the Fermi level. Okay, so all this calculation, it is done by density of functional theory. So here density functional theory and the reactive molecular dynamics is going hand by hand. And here you can calculate the charge distribution. Here is this one, okay, surrounding this state, and this is the charge. Okay, as you can see, as you go away from this sulfur defected state, okay, after 5 angstrom you don't see any charge. Okay, so whenever you a sulfur get pops up in the neighborhood region, this becomes metallic. Okay, so we give this a name called virtual filament. That is not a filament, it is like those bulk filament but not real filament, but it creates a metallic bridge, a conductive bridge between these two electrodes. Okay, Okay, I'm not going here. Okay, so this is the molecular dynamics study, and what we do that we apply electric field like experiment by step. Okay, so I have a MOS2, I have created lot of defects, okay, manually. These all are sulfur defects. Okay, then I apply electric field, positive, 0, positive, 0, like a sinusoid. And then I count the number of sulfur popping. Okay, so initially there is no sulfur popping. Okay, how it explains the memristor behavior? So sulfur popping means I am creating a conductive bridge between these two electrodes. Okay, so it is just like memristor behavior. So if you first increase the electric field, current is not flowing. Okay, there is no popping. Okay, now popping has started. Okay, so it increases. Then I have put 12 defects. So the maximum defect you can have, maximum popping you can have 12. Okay, so it goes up. Then 11, almost 11 popped state. Okay, so that means so many conductive bridge I have created. Okay, now I am reducing the electric field, but this popped atom, it is not coming back. Okay, now electric field is 0, it is holding. See, it is not coming back. Now I go to negative, extreme negative, then pop atom, it is going back to its original state and the number is reducing and it becomes 0. Then the second cycle, same thing is happening. And here also you can see some stochastic nature. This cycle is not identical with the other cycle. So the stochastic nature is also captured. Okay. And another thing we observe, that is, in the literature also, they say that in this kind of memory strip device, they study the thermal signature. Okay, they have a heat map and they show that this heat map, I mean, it is not, I mean, this device is conducting, so it is heating up, but the heat distribution, it is not uniform. Okay, it is concentric. In some place you have more heat and in some other place you don't have it. So here also we observe this joule heating. Okay, in order to bring the sulfur back to its original position, so here what I have done, we have heating the, the region which is close to that sulfur vacancy, and this heating is different from the on and the off. So unless I heat it up, it doesn't come back. Okay, so the joule heating and this non isotropic heating that is observed in the experiment, that is also explained by this molecular dynamics simulation. Okay, now let me just show you one video. Okay, so this is the setup process. You see, now you'll see here. This is the sulfur popping. Okay, now I go to this one. This is the other one. It is already popped. I have the opposite electric field. It will go down. See, it has gone down. So this is the molecular dynamics. If you have not aware about it, have not seen this thing, so here you cannot observe it by any kind of measurement. So that's why molecular dynamics is so much useful, that I can explain something where the experiment cannot reach. Okay, so these are called atomic snapshot. Okay, and also, I mean, experiment, they have shown the both the bipolar and unipolar action. So here you can see I am not going in the negative direction. So this is the reset switch. So still I can reset the device. So using molecular dynamics and this theory, that is the sulfur popping. Okay, I can explain both the bipolar and the non-bipolar switching. And in the initially this electrode, we took it like a LJ wall. There's something, this is a hypothetical fixed electrode. Now here I have put real graphene electrode. Okay, there also I have applied this kind of pulse, And here also you can see the movement of the sulfur atom up and down, up and down. Okay, so this is called full reactive simulation. So carbon, MO, and sulfur. So we have luckily the reactive potential for all of these three, and we can show this kind of resistive switching. Okay, I mean this kind of sulfur movement which ends up in the resistive switching. Okay, we have also tried, that is, you see the difference between the reactive force field and non-reactive force field. We have also tried with the graphene electrode, and the result is quite remarkable. Okay, so you can see that I have applied electric field here, that the postulate in the experiment they are giving that gold is coming and sitting there. So gold is coming, it is coming, these are the time step, but it is again going back, it is again coming, it is again going back, it is not forming the bond. Why? Because I don't have reactive force field available between MOS2 and gold. Here I have used the non-reactive force field. Here it is possible to combine both the reactive and non-reactive. Within MOS2 there is reactive force field, but MOS2 gold I don't have, there is no reported force field, so we have used the non-reactive one, the LJ force. So even we don't know that the atom is coming up, but it is not able to form the bond because that information is not there. So even deliberately we took a atom from gold and put it here, but it is going back. Okay, so it is inconclusive. We don't know that really what they are suggesting, that the gold atom will come from the electrode and sit here. There is a tendency that gold atom will come here, coming out. But since I don't have a reactive force field, this study was inconclusive. And that is the biggest challenge of this molecular dynamics of this kind of study, the absence of reactive force field. And it is very difficult. Right now, we are trying to develop such force field. We are studying this HBN based device. Okay, but the force field is not available. We are trying to develop it, and it is very, very difficult. Okay, thing to do. And as I told you, outside their Van Duyn group, hardly there is any success in developing reactive force field using their model. Okay, so unless they are developing it and releasing it for the community, it is very, these are very interesting study. Okay, but unless you have the reactive force field for certain material system, it is very difficult to do this thing. So what is the way forward? Again, I told you I will end this presentation with machine learning. Okay, so machine learning force field, it is the in thing. So what it is doing, so this paper, it was the first machine learning force field which wins SCM Gordon Bell Prize in high performance computing from Princeton University. So basically, I mean, again, it is one kind of reactive force field. So they are replacing the ab initio, that is the DFT force field, using a machine learning model. Okay, so this was the first group. Now there is lot of work even inside VASP. This is the latest one. Okay, they have this machine learning, they call it on the fly, but there are limitation also, like here for our type of problem, what we are doing, we are applying electric field, that I am applying force. Okay, so I need the charge information of the atom, because if I know the charge on the atom, then the electric field, then there would be a force. So many of this machine learning force field, they don't give the information of charge on the atom, so these are not suitable. So this is a very recent paper this year only. It is called SpookyNet. Okay, machine learning force field, and they claim that they have the option that you can get electronic charge. Okay, also spin, that could be learned. Okay, but they are very recent development, but these are very promising. Okay, because they hopefully it can replace the reactive force field, because developing reactive force field is a very big challenge. And if this development is there, I mean, lot of groups are working, it is moving very fast, and hopefully we can use this, okay, to solve our problem. Okay, that is the getting insight into the 2D resistive memory. Okay. And yeah, I just so thank you very much, and I will be happy to take some questions and any feedback of our work. Thank you. Yeah, Gilson, I am done.
Yes, thank you so much, Santano, for the
Very
great
long
talk.
time.
Yeah, it was a little bit longer than expected. I must say, was very interesting. So please, no problem. Yes, yeah, it was really very comprehensive. Also started from the basics, and then you got to in deep to your work. So I think was very nice talk. I mean, really,
Thank you.
really
Thank you very much. Yeah.
thank you so much, Santano. And well, we have a few
So,
questions.
do you have any question? Well, I can see the question.
Yes, one from Sergio Bumpi is from our university. He asks, what are the advantages of MOS2 with respect to other membership materials, with respect to the ever elusive problem of reproducibility or at the as-grown variability of memory stores?
See, actually, I mean, this is emerging area, and right now we are not in a position to say if MOS2 has any advantage over other 2D material. Always we start, most of the time, MOS2 is the most widely studied 2D semiconductor. Okay, and it is easily available. It is, as you probably know, MOS2 is before all of this thing 2D material began. Okay, MOS2 was used as a lubricant. Okay, so MOS2 is widely available material and most studied material. So whenever somebody try to do something new with 2D material, they study MOS2. Okay, so that is the only reason. But at this moment, uh, in the context of two-dimensional memristor, I don't think we can comment on if it has any advantages over other 2D material.
Okay, thank you, Santana. I have a question also. You can do like atom popping that will lead to resistive changes. And usually you look at applying electrical fields, right? But
Yes.
maybe could not also get insight and experimental data that help the modeling and understanding what's happening if it would be possible to do only I mean, instead of only applying electrical fields, you only rise the temperature, and then could it then also change the atomic structure and lead to atom popping or depopping, let's say so, and then you see what happens, activation energy and so on. If that could be something that could
Yeah,
help you.
so I can, it is little bit of chemistry somewhere here. I can explain you without not going very details. You can see the screen. My screen is visible or not?
Not now. I
Okay, I
cannot
can
see it.
tell you, explain you. So what is
Okay.
happening when sulfur get pops? It moves in a very symmetric position. Okay, and when we do analysis, we find this new position, the bonding of sulfur, because of the symmetric nature, the bonding of sulfur with the neighboring atom, it is much stronger than its initial position. Okay, because of that, this non-volatility is happening. Okay, that you switch it off, it is not coming back. So it has much stronger bond than the initial position. And
Okay.
just by applying a opposite electric field, it is very difficult to break the bond unless you apply some more energy through temperature. Okay,
Okay. So
that
it's a
is
more
the observation. And so in our framework, it is very difficult to model the exact joule heating. So we have modeled it kind of phenomenologically, that I am heating up that the neighborhood. Okay, so that I can loosen the bond a bit. That might happen because of the joule heating, and then also if I apply the electric field, it is coming down. So it explains this two things, that why joule heating is important and why it is non-volatile, because after sulfur moves there, it creates much stronger bond with the neighbor atom than the initial position.
Okay, thank you very much. And also a question, how much computational power do you need to run
Ah,
this technique? Just to
yeah,
have a guess, you know.
yeah, it requires supercomputer. So this package actually there is some issues normal molecular dynamics that we have used this lamps package. If it is non-reactive, those things now, because of the advances in the computational science, now that could be ported in GPU, that has become very fast. Okay, but this reactive one is not very scalable. Okay, anyhow, we have used a 500 cores in a superconductor 500 cores machine in CPU. Yeah.
And you can, if you that are watching over YouTube, you can type your questions on the chat there, and I will read them to Santanu if there are more questions. I don't know if there are more questions. And if not, Santanu, if you also could tell your email to the audience,
Oh
type
yeah,
it so that,
where I should type it is Shantanu, Santanu at, you can find me in Google. Okay, I should have written it at the front page.
no
Sorry,
problem. Yeah.
Shantanu at iisc.ac.in.
Yes. Yeah, as I said, people can find you on the internet and then can
Yeah,
send
yeah,
you
you
any
can
email,
say
any
now
questions.
everything. Yes.
I don't know if there are more questions. Just wait a second to see if more people ask at YouTube. Make questions at you over YouTube. I think there are no
Okay.
more questions. And again, Santano, thank you very much
Thank you very
for your
much.
talk. I really enjoyed
Welcome.
the talk.
Yeah,
Yeah.
yeah.
Yeah. Okay. So you must be also tired because you talk for more than 1.5 hours. So again, thank you.
No, nowadays we give lectures online 1.5 hour. My lecture is all 1.5 hours, and so
Yeah. Okay.
so we have habit talking.
Okay.
Okay, so
Okay.
thank you.
Thank you again. Yes. Bye
Thank
bye. And let's stay in touch. Yes.
you
Yes. Bye.
very much.
Bye.